โอเคครับ Good morning คุณการรดาครับ I saw you're coming to the class first. Okay, so you get an A plus from OM-316. Okay.
Oh, good morning. Thank you.
Very good. คุณภูสนิสาครับ Good morning.
Good morning ค่ะ
I mean, you guys sounds like you are just like wake up, just still stay in bed with your computers, on your laps. คุณสหภาพครับ Good morning. คุณเอมิกาครับ Good morning. คุณณัชนนท์ Good morning ครับ
Good morning.
Good morning ครับ
I totally forget all your faces already, so I hope that soon, okay, on the exam date, I will have a chance to see you guys happy face again. Okay. คุณนัชชาครับ Good morning.
Good morning ค่ะ
Okay, I wish you guys, 1, 2, 3, 4, 5, 6, 6 students here with me today on the 12th class. We get an A. And Kun Thammonwan is coming. Okay, maybe, you also get a day. Kun Thammonwan, good morning, club.
Good morning ค่ะ
I don't know which one of you having Apple Macintosh, okay, and trying to do the remote access to the computer lab and has problems. Is there anyone having a problem getting a remote access to the computer labs? Well, just let me know. I mean, maybe after the class, I will help you to come across the problems. Okay. Good morning, good morning. Okay. Today is the 12th class already, and we are coming to the end of the class. We have 3 more classes. After Songkran Festival, okay, I will devote 2 out of 3 for the chapter 7 Bock and Jenkins Arima models, and last class will be on the combining forecast. Okay, the last class will be very short because I have just only a brief talk on combining individual forecasts together and make a better forecast. Okay. So today I will try to complete chapter 6, which is decomposition technique. This technique is very easy to comprehend and easy to work with. I think you can do it by using Microsoft Excel. Even though you can run, in practice, you can run decomposition technique by using forecasting software like Forecast. But as usual, before we move to chapter 6, let's check on the homework. Okay, I think I gave you homework number 9 already. Am I right? Yeah, homework number 9. And last week I asked you to run Costco quality time series and determine 2 MLR models. And in the end, you have to tell me which model is more appropriate to be used for forecasting purpose. The first model is running revenue of Costco versus 9 independent variables: DPI, per capita, PCE, CPI, GDP, Fed fund rate, time lag 1 period, Q2, Q3, Q4. In practice, actually, you might, run across each individual variable, and you can, add that variable to the model one at a time. Okay, but in homework number 9, I gave you all the 9 variable already, and I want you to take a look at regression models and try to solve the problem of serial correlation and dealing with seasonality, at the same time. Okay. The second model is decentralized revenue versus PCE, CPI, GDP, Fed fund rate, and time lags for one period. For the second model, you take, short-term fluctuations in the data out. This is the one to cause a time series to be volatile. Okay, so you take seasonality out first, and then you run multiple regression and see how it goes. Okay. Let's see. Okay, out of 27 students, 23 handed in today, and there are 2 persons turning in maybe today, by today. Okay, I think I looked at one of your homeworks, Kun Kitapat. Okay, and I saw what you did. I think the process is correct. Okay, you run multiple regression first, MLR revenues. Okay, come up with, revenue versus 9 independent variables. And here you have MAP of 4.45% with R square of 97.63%. This means that the relationship between 9 variables and revenues can help you to explain variation in revenue around 97.63%. There are just only 2 and 37% that cannot be explained by these 9 independent variables. Okay, which is very good. Okay, 97%. Here you have the F test. Okay, I think Kun Kitapat misunderstood about the overall F test here. When you look at the overall picture, you try to validate the model, and you see the F test here. The hypothesis for the F test is beta 1 up until beta 9 equal to 0, right? And H1 is at least 1 beta is not equal to 0. And you see here that F test is to 14.69, which is high enough, cause you to reject the null hypothesis. And when you reject the null hypothesis, it means that, in the overall picture, the model is valid because you have at least 1 variable related to the revenue. When you go down to check individual independent variable, you can see that some of the variable pass the hypothesis, meaning that you reject the null hypothesis. For example, here you have CPI, you have Fed fund rate, okay, you have time lag with 1 period, you have Q4, but the rest you fail. It fails to reject the null hypothesis, DPI, GDP, PCEs, Q2 and Q3. When you move down to check relationship by using correlation coefficient in the table, you see that here you have DPI per capita. This is revenue, right? So you have DPI, it values of R around 0.84, which is moderately high. But when you check with the PCE, relationship among independent variables is 0.99. Okay, it's almost the same variable. It carries pretty much the same information to explain revenue. Okay, and also CPI 0.97, GDP 0.99. So DPI per capita is highly related to PCE, CPI, and GDP. And the relationship amongst independent variables are even higher than relationship between DPI per capita and the revenue. Okay, this causes a major problem in multiple regression. Can anyone tell me what is the problem? Can anyone would like to give a shout, please? What is the problem here that you see? You see?
multicollinearity ค่ะ
Yeah, multicollinearity, exactly right. Okay, thank you. Okay. So you see multicollinearity problems, the result of the t-test conflict with the result from correlation tables here. Okay, you have to solve the problem. Okay, but let's hold on to this problem for a moment. When you move down to look at the accuracy measure, you see that the model is very good, very accurate. Okay, 97.63%. When you look at the statistic, it's 0.29. It's far less than 1. Okay, it's much better than using basic naive model. Okay, if you look at AIC and BIC, okay, it is 977 and 979. You don't see changes here, different here. But if you start developing the multiple regression from using just only one variable, 2 variable, 3 variable, up until the 9 variable, you will see that AIC and BIC would drastically decline. And this is the end point, okay, 977 and 979. DW 1.63, okay, using rule of thumbs, you can see that 1.63 is still, close to 2. So the result could be no serial correlation problems, or if serial correlation problems occur, it's still weak, okay, it's still indeterminate. So in this situation, you can rely on all the accuracy measures. Okay. But you have to solve the problem because of the multicollinearity. Okay, by solving the multicollinearity problem, you run stepwise regressions. Okay, you run stepwise regression. Here you have just only 1, 2, 3, 4, and 5 variables. You have R square of 97.53%. Okay, when you look at the original 9 variables, you see 97.63. You drop 4 variables, but accuracy dropped just only 0.1%. What does it mean here? Okay, all the 4 variables that are kicked out carry pretty much the same information of the 5 variables that already in the model. Okay, so they are redundant. So that's why they can get kicked out from the model. Okay, you run and check the F-test. F-test here 4.402, which is very large. Definitely you reject the null hypothesis for the overall check. Okay, at least 1 beta is not equal to 0. And when you go down to individual tests, you see that now DPI per capita, which is highly correlated to PCE, CPI, and GDP are kicked out. Okay, CPI also kick out. Okay, they carry same information with the DPI per capita, PCE, and GDP. Okay, that's why they kick out. Okay, Q2 and Q3 also kick out because they not have much effects to the revenues. Okay, in this situation. Okay, when you look at the DW, it's 1.83. The value is even close to 2 more than the previous model. Okay, so definitely accuracy measures here are valid. You can see that AIC, BAC step up just only, a minute ago is our previous model is 977 and 979. So, even though you get rid of 4 variable, it doesn't affect the values of AIC and BAC significantly. Okay, MAP is around in the 4 to 5%, which is pretty much the same as MAP for the revenues. Okay, the other move up just only less than 1%. Just like the way you look at R square, which show the accuracy of the models. So before running stepwise regression, you have 97.63. You get rid of 4 variables, it dropped just 0.1%. So it insignificantly dropped in the forecast ability of the models. Same for RMSE. Okay, you have 1, 2, 6, 3 here, and when you drop 4 independent variable, it go up just only 20 points. Deals remain pretty much the same values, 0.29. Okay. So this is the more valid models than MLR with revenue. Okay. So this is the model that you should use if you want to incorporate seasonality into the model. Next one is you run MLR for decentralized revenue. You have 1, 2, 3, 4, 5, and 6 variables. Okay. In this model, you take seasonality out of a time series first. You want to deal with fluctuation, short-term fluctuation in the data in the series, but you still use enter method, meaning that you force all 6 variables to be in the models. You have accuracy of around 99% here. Okay. MAPE dropped to 2.51%. Definitely, you see high accuracy in the models. Do you know reason why running MLR for decentralized data is seem to be more accurate than running MLR for original revenues or the first model? Can anyone tell me, please? What is your observation?
That is because MLR doesn't capture the seasonality.
Yeah, I consider your answer correct. Okay, here you look at a series, you see lots of fluctuations. So when you have fluctuation or versatile in the data, it's more difficult for the model to capture the data, right? But when you get rid of fluctuation in the data, you see a smooth line here. So it's easier for forecasting model to capture a time series, right? So that's why in general it should be more accurate than original MLR with original time series. Okay. So this is my observation for these examples. Okay, and I think in general it be this way, but it depends. If you be able to identify very important independent variable in the models, you cause regression model to be very accurate already, even though you incorporate seasonality, in MLR models. Actually, when you look at MLR revenues here, accuracy around 97% already. I think 97%. If you compare with your marks when you do the exam and you get like more than 95%, I think your mark is outstanding already. Same as forecasting model, when the accuracy show that it beyond 95%, is outstanding. It's a very good model already. Yeah. Okay, let's go down. This is 99.02%. Okay, when you look at overall F test, you have even bigger values than the previous MLR models. Yeah. And you reject null hypothesis, at least one variable related to the decentralized revenue. But again, since you use enter method, you force all 6 variables into multiple regressions. There's some situation, there's some independent variables which are highly correlated to other variables. For example, DPI. You see that DPI per capita relationship with decentralized revenue around 0.91. Okay, but it has very strong relationship with PC 0.99, CPI 0.97, and GDP 0.99. Same for CPI here. It related to the seasonalized revenues around 0.80, but its relationship with the DPI per capita 0.97, PCE 0.94, GDP 0.94. Definitely, here you have multi-correlative problems. But when you look at DW 2.3, it's still close to 2, right? So our accuracy measures here are reliable, and you have accuracy of 99.02%. You have AIC BAC of 916. Okay. Now with stepwise regressions. Okay. Here you have just only one variable left, and you have 98.87. Okay. Accuracy drops just only 0.2 or 0.3% only. You have still very accurate models here. Okay. And MAP just only 2.6%. You have F test of 4,800. Wow, very, very large values. And you have in this situation just only one time X here. Okay. And again, you have 2.63. I think the result still indeterminate for the case of serial correlations. So accuracy measures here are reliable. Okay. So in the end, you have 98.87. Okay. So when you compare all the 4 models here, including original revenues with enter methods and stepwise methods, and decentralized MLRs, enter and stepwise methods, which one is the best one? You can see that so which one? I need a volunteer to answer my questions. I don't want Mr. Ekajit to answer this question. I want you guys to answer my questions here. Which one is the best one? Kun Nachaครับ, do you want to try to answer my question? Kun Emikaครับ, can you try to answer my question? Which one is the best one based on your investigation here?
Stepwise regression.
The stepwise regression of which model? Of which models?
Decision.
Yeah, stepwise regression with the decentralized revenue, right? the last model, right? The last models, because there's no serial correlation and there is no multi-correlative problems. Okay, you have accuracy around 98.87%, and you have MAPE of 2.6%. Okay, actually, if you have, if you want to compare between MAPE of these models and the model that you deal with seasonality directly, okay, you might have to, if you want to make sure that this model is the best one, you might have to multiply back the seasonal indices, okay, to come up with the final forecast and run MAP to check it one more time. But the accuracy, I think, in general, is remain the same. You're gonna get the same values of MAPE even though you do not, deal with seasonality or you deal with seasonality. Okay. But there is one observation here. I have to apologize to you guys. Okay. I just realized that here you have heading, two heading rows. And when you have two heading rows, it's gonna cause forecast X to set the initial value for each variable to be zeros. Okay, and it's gonna cause the outcome of the model to be slightly different from what it should be. Okay, so to make correction here, you have to, let me go back to the original series. Okay, so I have to get rid of one of the rows, okay, and start the first period at Q1 of 2005. Okay, so this is my correction. Okay, so sorry that I did not recognize this beforehand. So when you run regressions and see the output, you see the first values go down to zeros, which is not, this should not be the case. Yeah, and it's caused by the hidden rows, in the labels. So if you make correction and we run MLR, you get more correct answers. But it doesn't change your conclusion. Okay, the accuracy measure turn out to be slightly different from what you obtain when you have zero values in the beginnings. Okay, let me rerun the multiple regression using stepwise here. Okay, so I move to revenue first. Okay, it's revenues, DPI per capita, PCE, CPI, GDP, Fed fund rate. And this is revenue T minus 1 or one time lags, and Q2, Q3, and Q4. So let me rerun it to show you. Using forecast X. This is quality data, and I want to forecast just only 4 quarters ahead for operational plan. And using stepwise, set MACLAG to be calculated to be zeros here. AIC and BIC, DW here. Accuracy, root mean square deals, and if you like MAE, that's fine. You can take MAE. Okay, and then you're ready to make a forecast. And if you like to see which forecasting model forecast X come up with, okay, to fit DPI per capita, PCE, CPI, GDP, Fed fund rate, time lags, and Q2, Q3, and Q4. Okay, in case that you want to forecast future values, you can click on standard output. It will show you the name of the fit variable, fit models here. Okay, let me take it for you guys. when you look at the standard output, you see when you want to make a forecast for the next 4 period, it come up with, it automatically come up with the fit models and use these model to make a forecast. Okay, but we would like to look more on the audit output based on using stepwise regressions. You have 1, 2, 3, and 4 variable left, and accuracy here is 97.33. You have 4.29% of MAP. Overalls of F-test 465. And you have DW of 1.94, very close to 2. So there's no serial correlation problems. You have AIC, BAC around 960. Deals of 2 to 8 here. When you move to this slide, okay, without the hidden rows here, you run forecast X. And make a forecast of 4 period here and run stepwise. You like to see just R square, that's fine, you can take it here. Accuracies and the report. Okay, you have just only, you have 1, 2, and 3 variables. I think it's a bit different from what you got when you have 0 values for the first data series. Okay. But here you have 2.45. Okay, the previous model that you run, you have 2.60, right? This is 99.09%. You have 1894 for the F-test. Definitely you reject the null hypothesis. And okay, without multiplicity problem, you get DW of 2.12. Okay, and AIC, BIC go down to 886, 818, 888, right? Even though you have deals of 0.74, but when you look at others accuracy measure, it's point out that this model is more accurate, right, than the one which incorporates seasonality. So your decision about the most appropriate models for this particular time series remain the same, with or without the hidden rows in the headings. Okay. So if you like to make a small or minor correction, that's fine. You can redo it and submit it to me. I will tell PMI not to deduct any point from pre-submitting the homework. Okay, but if you want to keep it like this, that's fine. But this situation just hints you that regression model is sensitive to the data. Okay, just like the mean. Okay, it's sensitive to the outliers. When you have zeros, it looks like an outlier, right? So that's why MLR is sensitive to this 0 or blank values here. Okay, in the situation that you want to compare the final forecast, okay, with the original series, you can make a copy of fit data here. This is the fit data for the deseasonalized revenue, right? So you have to make a copy of this one and paste it right here. Okay, this is deseasonalized. Maybe I put it here. Okay, and then you have to multiply with the index, right? Because you take out the index, okay? But I think I erased the index column already, so I need to find the index. Okay. So what should I do? What should I do? It's easier because when you perform this line, you have sorry, you have seasonally adjust revenue equal to the revenues, okay, over the index, right? So the index is actually revenues over seasonal adjust revenues here. So let me bring the original revenues from here and paste it right here. Okay, now I want to see index indices. Okay. So it is actually this one divided by the fit, no, sorry, you know, the fit one, wrong one. The index let me put the index here. Okay. Oops. The index here is equal to this one divided by the seasonal revenues here. Okay, and I can drag the cell down. Oops. One moment. Let me. Why we don't choose stepwise with revenue model? Stepwise with revenue because I saw that stepwise with decentralized have the W around 2.63, which with it will have seasonal problems. Okay. Let me check. Okay, it depends. Okay, if I make decision based on rule of thumbs, okay, I see that yeah, 2 zeros and 4, right? So if you know in your situations, okay, and this is DL, right, and this is DU 4 minus DU 4 minus DL. It depends. Okay, I use rule of thumb and I make judgment quickly, and I see that maybe 2.63 somewhere here. You know, it's in the indeterminate. Okay, meaning that problem is not that clear. Okay, so you can still claim that the results are reliable. But if you look into the details and you come up with DL and DU, for example, you have DL of maybe 1.3 and DU is like 1.4, something like that. So you make a you know the range of the 4 minus DU, which is 2.6. Or well, maybe if it is well, even though these two values still right, 2.7 here, 2.63 somewhere here. It depends. Okay, if you read the W tables with maybe how many variables that you have left, 4 variables or 6 variables with k equal to 6. Okay, and with n equal to, I don't know how many data you have. Suppose that it has 100 and you read DL and DU. Okay, so you can make a clear judgment if 263 is in which area. If it falls in this area, definitely you say it has negative serial correlation problems. If it definitely in this area, you call it positive serial correlation, then you can make a decision that the model is not valid. But if 2.63 is somewhere here, the problems still in the terminate, you still claim that the model is still valid. Okay. But keep in mind that you should watch out for serial correlations. When you make a forecast for the next year and when the actual value of next year come in, you revise the model. Point of concern is the serial correlation problem. Okay, it might occur. ครับผม I hope my answer will clarify your doubt. Okay. Thank you, Kap. Thanks for the question anyway. Okay. Your question give me energy to teach. So if you keep quiet, I will feel sleepy, more sleepy, and more sleepy. Maybe in the end, I am sleeping while teaching, but you don't know, right? You don't see my face, you just hear my voice. What is the difference between negative and positive serial correlation? I think you should go back to read chapter 4. The negative serial correlation occur when you check on the errors, right? You can plot errors versus X or versus Y. Up to you, or Y hat, sorry. So if it is something like this, definitely you know right away, right? You know right away that your forecast will be overestimate, then underestimate, and then overestimate, and then underestimate. Okay, so in this situation, you have negative serial correlations. Okay. But when you have these situations, okay, the movement of errors is somewhat like a wave-like patterns like this. You have negative error followed by negative error, positive error followed by positive errors. These situations, you have what it called positive serial correlations. Okay. When this situation occurs, based on the assumption of regression, you know that you take a sample, random sample, right? So you should have X and Y here. Pattern of coordinate to be random. Okay, when you run regression here, the errors, which is the actual value subtract by the predicted or forecast value using multiple regressions. When you plot errors and X or Y hat, it should be random. Okay. So if this situation occurs, the calculation of the t-test, the f-test, the r-square, okay, will be as usual. There's no problems with the calculations. So they are all valid when you read the values. But when you read that there is a negative serial or positive serial without any mathematical proof, okay, I don't want to get into the proof, okay, but the conclusion is that the calculation of error caused the error to be smaller, maybe because of the cancellation problems, okay, that occur. So it's gonna cause the f-test. Okay, the f is MSR over MSE, right? So this is SSR, freedom SSE. It's gonna cause SSE to be smaller than it should be. So when SSE is smaller, f-test gonna go bigger. And definitely you tend to reject the null hypothesis when f is bigger, right? So it's gonna cause f value to be exaggerated. Same for the t-test. For example, if you have like b1 minus beta 1 over s of b1, okay, this one will be smaller, okay, than it should be. So the t will be exaggerated also. Same for the r values. The r value is SSR over SST, right? It is SST minus SSE over SST. This one minus SSE over SST. This one will be smaller. When you have one minus very small value, you're going to get very large R squared. So it causes, when you have this situation and this situation, it's going to cause the test statistic not reliable. So that's why I asked you to look at DW first, whether you can go through with the accuracy measures or not. So the diagnostic of this situation and this situation can be done by using the DW values. And when you have DW equal to 2, there's no problems with negative serial correlation or positive serial correlations. But when you have DW go down close to 0 or go up close to 4, then you're going to have positive serial correlations and negative serial correlation. And when it occurs, like I said, it's going to cause this accuracy measure, this statistic to be unreliable. ครับผม So are you okay with my answer? Yes, thank you. Give me big smile. Can you give me big smile, please? Okay, let's continue. Now, you have index already. This is the fifth data, so you're gonna have the final forecast, right, for the case of the seasonally adjusted level. Okay, so I say this is the final forecast. Okay. So I just multiply back the fit values with the index, right? So it's gonna be equal to this one. Oops. This one multiplied by the index right here. Okay, this is the final forecast. And when you wanna compare final forecast with the revenues, the original series here. So let me copy of this one to this one, right? This is the final forecast. Oops. I think I have to paste it with using values. Oops. Can I do this? No. But anyway, and then I can calculate the errors, right? Very good. Okay. The errors or the residuals here is the original series with the final forecast, minus the final forecast. But I want to calculate MAPE, right? So I would like to have the absolute of the errors divided by the revenue, right? The original series. So it is actually and divided by the revenues here. Oops. Okay, and then I can forget the absolute values. ABS. So let's move it down to make correction of the calculated values here. Now you have MAPE for final forecast to be equal to average of this one up until this one. (2.45%). Okay, so what I did is to show you that when you run the seasonalized data, okay, and you get the R square here, the MAP here is 2.45%. Okay. After you multiply back the index, okay, to come up with the final forecast, and you check the errors, MAP still the same. Okay, so you can use that MAP to make comparisons with another models. Okay. So how good this final forecast is? Let me see. It is very accurate. 99.09%, I think. Very good. The reason that we have a very accurate model in MLR here is because we have very important independent variables in our models. Okay, if you cannot find very important variable that can explain variation in the revenue, then you have a problem because the R square will be very low. So this is one thing that you have to keep in mind. Keep searching for important variables. Okay. And this is going to help you in terms of running multiple regression for your term projects. You have a variable of interest. You have to keep searching for important variables and maybe try to run regressions, simple or multiple regressions. But as I told you that, we use the KIS, keep it simple principles. You want to identify the least number of important independent variables to be included into the models. You don't want to use a very complicated models, and you don't want to run into trouble when you make a forecast and you have to keep searching for the forecast values of independent variables. Okay, that's it for the homework. I hope that I clarify many points that you have in mind when you run the exercise number 9. Okay, if there are any questions, feel free to ask me now. If not, I will move to chapter 6. No question ใช่ไหมครับ Okay, so let's go to chapter 6 together. Okay. Chapter 6, the time series decomposition models. By its name, decompose, you disaggregate, right, components in the series or in the models. Here you try to identify the trend component, the seasonal component, the cycle component in the models. We don't want to decompose the irregular variation in, but we want to smooth things out. We want to get rid of the irregular variation. And when we make a forecast, we recompose trend, seasonal component and cycle component together. And we assign the irregular variation to be 1, or there is no irregular variations in the future. Because it happened once in the past, it's not gonna happen in the future, right? We're not gonna forecast that there will be the next COVID-like pandemics, right? That cause the effects to our business. We don't want to make a forecast that will be tsunami that occurs, right, in the Pacific Oceans that caused the situation that happened like 16 years ago, right? Catastrophic situation. Anyway, time series decomposition model is one of the oldest models in forecasting arena. Okay, but it's still very popular nowadays. Actually, when you look at chapter 3 models like Ho and Winter, when you want to deal with trend and seasonality directly, you have 4 equations in Ho and Winter, right? It's very complicated. But when you run decompositions, actually there are 2 approaches. The first one is the additive approach. You have additive decomposition. You can write an equation, algebraic equation of the decomposition model to be y, which is variable of interest, to be trends plus cycle plus seasonal plus irregular variations, like this. Okay. The second approach is the multiplicative decomposition. You have y written as t times c times s times I. In chapter 6, we are dealing only with the multiplicative forms of decompositions. Why is that? Because it's consistent with the way we look at a time series. When we read the trend has the original values, right? If you have a unit, the trend, it will be unit. For example, 50, 100, 120, and 150, and so on. Period. 1, 2, 3, and 4. When you plot a series, you're going to have this kind of trend. But the cycle component and the seasonal component, you read it as the index form. Indices form. Okay, and when you read C greater than 1, you see that with this situation, the business cost your sales or number of customers that come into the come into your office to be more than the average values, right? More than the trends. So EFC is less than 1. The economic situations cause the sales to be lower than the trend, lower than the average of the year. Something like that. So you have index out of 1. Same for the S. When S is greater than 1, you have a high seasons. When S less than 1, you have a low season. It's very easy to comprehend. It's actually different from the additive form. When you have additive form, here you have original unit for all components. And when you read C equal to 150 or like 90, it's a bit difficult to make interpretations, same as seasonal effects, right? So in our class, we prefer multiplicative form. But in practice, in real world, you have both models. And sometimes you have multiplicative form to be superior to additive form. Sometimes you have additive form superior to the multiplicative form in terms of forecasting purpose. It's up to you to make decision which one you are going to use. Okay, so let's now scope our talk to just only y equal to t, c, s, and I. Okay. The reason that decomposition is still popular nowadays because it provides excellent forecast. You can see in many situations, it gives a very high accuracy, of the forecast values. Easy to understand. Like I said, it consistent with the way you guys or business managers look at the data. Right? And there are trends, cycle, seasonal components that affects the data, affect the demand, affect the revenues, affect the number of people coming to use your service. Okay. And it's very simple models, right? As compared to more complicated model like Ho and Winter. Actually, I would say it is a strong competitor to Ho and Winter models. Okay, as an example to explain the composition model, this is private housing start time series start from Q1 of 1965 to 1999. And when you plot a series, you see that there's a positive trend, slightly upward trend. Okay, let me write down here. Okay, and there's a long-term effect. Okay, you have data cover around 35 years. So the waveline patterns along the trend line is considered to be cycles. And in the cycle, you see repeat pattern years after year. This is seasonal patterns. Right? So you can write an equation of y equal to t, c, s, and I. correspond to decomposition series. Now, decomposition procedure start with first, remove the short-term fluctuation from the data so that you can see only the long-term components. What are the short-term fluctuations in the data? Definitely, you talk about S. And if there's regular variation, it is. Okay, so you have S and I to be short-term fluctuations. And how to get rid of short-term fluctuations? You apply MA, moving average, to the series. Okay, and this is just only to get rid of short-term fluctuation. It's not like to use MA to make a forecast of future values. Okay. So for quality data, you perform MA4. Okay, and for monthly data, you perform MA12. So this is a picture of the time series of interest. Okay, and suppose that is quality data. You have the first data of Q1, Q2, Q3, Q4, Q1, Q2, Q3, and Q4, and so on. Now you have Y. Okay, this is period. And this is actual data. You have Y1, Y2, Y3, Y4, Y5, Y6, Y7, and Y8. Then you can perform MA4 here. Okay. Now MA4 that you obtain, you put it in the middle of the 4 data that you average. Okay. So here you have Q1, 2, 3, and 4. So what is the middle of these 4 quarters? Is actually at period 2.5. So you have MA4 F of, no, not F, sorry. MA4 of 2.5, right? You put in the middle equal to Y1 plus Y2 plus Y3 plus Y4 divided by 4, right? And then the next MA gonna be in the middle, right, of the average value between Y2 and Y5. So you have MA4 of 3.5. You put in the middle of the data that you average. You kick out Y1. You have Y2 plus Y3 plus Y4 plus Y5 divided by 4. So the MA values continues. Okay, MA4 at 4.5 period at 5.5 period. You put in the middle. And definitely when you have monthly data, you have Jan, Feb, March, April, May, June, July, August, you have September, you have October, you have November, and December. You perform MA12. And the first MA that you're going to put it in the middle of the data that you average, right? 1, 2, 3, 4, 5, 6, you put it here. MA12 of 6.5 values. And then MA12 of 7.5 here. Okay, the reason that you put it in the middle of the data is because you average them. You want to get rid of fluctuation, right? You want to smooth the short-term fluctuation. Okay. And this is the formula. Okay, I perform calculation to show your guy already. So this is MA for quarterly data, and this is MA for monthly data. Now, when you want to use the moving average values, you have to adjust them, okay, to be consistent with the original quarter. So you have to perform another MA, but this is MA2 of the two adjacent moving average. So you perform CMA. So this is CMA. So you average the two, you have CMA. Again, you put it in the middle. You have CMA of quarter 3. To be this, and then CMA of quarter 4. So the quarters here, the period here are consistent with the period that you used originally, okay, in the beginning. So for the even number of periods, you need to center the moving average. The CMA for the time period you call CMA sub t is found as, okay, MA of t and MAT plus 1 divided by 2. Right? And in the end, after you do the all calculations for the full period or for full quarter, you lost 2 data in the beginning and you lost 2 in the end. The 2 period that you lost in the beginnings, it doesn't matter because it may be, you know, if the first 2 data, right, in the series, and is far from the present period, but the 2 in the end will be more important. But anyway, when you want to make a forecast, you can make a forecast of the data that you lost, okay, after you come up with trends, seasonal index, and cycle index. So this is the first 2 procedure. You perform MA and CMA. Let me erase the notes and move on. So for a particular example, so you have the first year, the second year as quality data, right? You perform in terms of writing in Excel, okay? There's no 2.5 cells, right? So the common practice is to put in quarter in period number 3, but you have to know yourself it is not in period 3 yet, it's in 2.5. And then you perform CMA, you put it the same place. Start at period number 3 and move on. What is the CMA? CMA represents the seasonal data. You get rid of seasonal variations, as well as if there is any irregular variation, it all smooth out. So let me show you how to do it by using examples in Excel. Let me bring it example seasonal data. Okay, this is the one that we use in chapter 1. I think you can go back far back in the past. It's like long time ago, right? Chapter 1 of OM-12. Bring it in. Here, you wanna do MA first, MA4. This is quality data. That's why you perform MA4. You want to smooth out data and then you bring into the middle of the data that you average. This is MA4. Oops. MA4. Okay. So since there is no 2.5 cells here, so I just use period number 3 and put the data in there. Okay. Average of these 4 values, right? Okay. Am I right? Until B17. Okay. And then perform CMA to adjust the quarters. Okay. So you have average of two adjacent MA right here. Up until here. Okay. So this is center moving average, which has no short-term fluctuations. Let me high MA flows. And plot two series in comparisons. You can see that original series you have seasonal, and if there's some random fluctuations is in there. But when you perform CMA, you smooth things out. You get rid of all the seasonal effect and if any irregular variations. And like I said, you lost to data in the beginning and you lost to idiot. That's fine. So this is how you come up with the CMAs. And when you write it in algebraic form, you have original series to be T, C, S, and I. And for the CMA, you get it off short-term fluctuation already, so you have T and C, right? You have just only long-term effects left in a series. Next step is to find seasonal indices. Okay, so what you do, you compare the actual values of any time period y sub t with the satellite values at the same period. So you have SF, seasonal factors, and SF sub t is YT over CMA sub t. I think you will be confused, somewhat confused, I think, in these situations, because when I write an equations, you have y, which is t, c, s, and I, and you divide it by CMA, which is t and c. You see, you get rid of TC above for the numerator and the denominator, you get S and I left. Okay. Don't get puzzled, because in the beginning you get rid of SI and you come up with the SI here, but in the beginning you want to smooth, you want to come up with the models to represent the long-term movement. And then you divide original value with the long-term movement, you get short-term movement. So this is how you come up with seasonal factor. Seasonal factor reflects your cells. Okay, if for a particular quarter you have SF greater than 1, it indicates that in this quarter your cell will be greater than a yearly average or greater than a trend line actually. And when you have SF less than 1, it indicates a period in which your cells less than yearly average. Okay. For swimmer example that I showed you in the tables, for period number 3 here, let me move back to number 3. You have the original series y as 20, and then you divide it by CMA3, where CMA3 15.25. You get SF of 1.31. And SF4, you have Y4 over CMA4, you have 0.76. Okay, it reflects that for quarter three here, your sales is greater than the yearly average, greater than the trend. You have high seasons. And for number 4, you have definitely low seasons. So let me do calculation and show you here. You calculate SF. Okay, so you have SF number 3 here equal to sales divided by CMA. Yes, SF. In theory, seasonal index for each quarter should be the same, right? Should have you, when you do the calculation, you should have the same values. But this is the real situation. You have data with fluctuations, okay, and business circumstance for each quarter, each year, still different. Right? So that's why it's typical to have slightly different values for SF in the same quarters, but still reflect the same situation. For example, you have SF of quarter 3 of 2018 of 0.67. For quarter 3 of 2019, quarter 3 of 2019 is 0.79. Okay, they both reflect that this quarter you have low season in your sales, right? And in 2020 you have 69, okay, low seasons. But the different numbers reflect the different business situations. It reflects randomness in the series, okay? So what you have to do next? Let me color each quarter so you see what I'm doing clearly. Okay, let me use this color for quarter 1. Okay, and for quarter 2, maybe a green colors. Okay, for quarter 3, maybe use a blue colors right here, light blue colors. Oops. Oh no, sorry. I did it wrong. This is quarter 3, right? And quarter 2 is the green one. Okay. For quarter 4, let's use which one? The gray colors here. So you see different quarters, right? Different situations. For the 3rd quarter, you have low sales. For the 4th quarter, you have sales around the average values, yearly average sales. Definitely for 1st quarter, you have high sales, okay, over 20% more than average values. Okay, now you have to calculate seasonal index. I would say this is S of 1, S of 2, S of 3, and S of 4. Okay, seasonal index of quarter 1, quarter 2, quarter 3. What I do is to average the seasonal factor for the same quarter. So for quarter one, I have March of 18, March of 19, March of 20, and March of 21 divided by 3, right? I averaged it. Okay. For quarter two, I have June of 9, June, I have quarter two of 2019 plus quarter two of 20s plus quarter twos of 21. And quarter three, go back to 18s, 19s, and 20s. For quarter four, I have '18s, I have 19, and I have 20s divided by 3. Okay, this reflects the seasonal index. Okay. In case that you have a long time series, you will have many more SF for each quarter. You can get rid of, you can rank the values for each quarter and you get rid of the highest value and the lowest values. This way you get rid of like outliers in the data, right? And then you can just average the rest. So like I said, you have SF here, SF still carries S and irregular variation or random variation in the data, right? So that's why you need to average the data. So you get rid of irregular variation or random variation. You come up with just only the effect of seasonality here. Here we would like to have the totals of the effects for 4 quarters to be 4. Because we want to have reference values for each quarter. If there's no effect of seasonality, your cell will be equal to S will be 1, right? There's no effects. Okay, you might have to adjust each index. Okay, the way you make adjustment is called you normalize the index. Okay, to have to make the total of index to be 4. Okay, so what you do is S1, S2, and S3, and S4. Okay, so you have the original index multiplied by I would say divided by the sum. Okay, I want to fix the sums here. And then you multiply is by 4, right? To adjust the index correspond to the total of 4. Otherwise, it's gonna be difficult to make interpretations. Because you sell 1.26 out of 396. When you make comparison, it's a bit difficult to comprehend, right? How high is the highest? How high is the index? But if you put it like total of 4, then you make comparisons and it's easier to understand. So I move down. Here I have the sum of index to be 4 already. So if there is no effects of seasonality for each quarter, your cell will be 1, right? The index will be 1. No effect of seasonality in this situation. So I obtain the index for each quarter already. I put it here. So this is the S. Actually, this is the first component that I come up with. Okay, let's make a copy one more time. Oops. Because I do the calculation here, so I need to copy just only the numbers. Otherwise, it's going to be changed. Okay, here is the index. And in case that, let me move it down. I want to make a forecast for 2022. I can just copy the index to Q1 to Q4 of 2022. Because the seasonality, the effect of seasonality is the same, right? For the first, the second, the third, and the fourth quarters of each year. This is the index that I obtain and I use it. And I gave it to you, right, in earlier chapters, in chapter 1, chapter 2, to decentralize the data. But this one is obtained from decomposition techniques. And another techniques that can obtain the seasonal index is the whole winter. Okay. Next is the trend cycle effects. Okay. Let me stop here because it's 10:37 already. So you should need a break, right, you guys? You're tired already. Listen to my talk for the half and a half. An hour and a half. So take a break. 15 minutes and come back. I will tell you how to obtain the trend cycle and in the end make forecast out of each component here. Okay, so I stop the record. Okay, let's continue our talk with the decomposition models. Okay, and if anyway, let me hide my videos and share the screen. Where is it? Okay. Let's go back to the lecture note for a moment. Okay, you calculate SF. Okay, and SF is actual data over its correspond center moving average. And SF reflects the effects of seasonality for each seasons. But with the random variation in the data, you have, even though it has the same effect for each quarters, but the value of SF for the same quarter will not be equal because of the random variation. That's why you have to average seasonal factor for each seasons. And the sum of the seasonal factor for all seasons should equal to 4 for quarterly data and 12 for monthly data. If it doesn't, you should normalize the index by multiplying each values with the ratio of number of periods to the sum of the average seasonal factors. Okay, I did it for you guys to see already, so I'm gonna move it. Table 6 that to represent example of time series decomposition of the private housing starts. Okay, I think this is the time series that we use to explain how to separate each component part, in a series and then recompose parts together and make a forecast. here is the original series. Okay, you first perform MA and come up with CMA. Okay, in CMA you lost to, in the beginning you lost to in the end. And from this CMA you calculate SF, and SF is the PSS over the CMA. You get the value of SF here. And then from the SF you calculate seasonal index. Okay, and then you have to calculate the trend. You have to determine the trend and determine the cycle factors before you come up with the forecast values. This picture shows you the values of time series, original time series in the dashed line. You see that it comprises of the long and the short-term fluctuations. But when you have CMAs, you get rid of fluctuations. Short-term fluctuation already, you come up with movement along the trend line, which is a long-term fluctuation. And based on a very long historical period, you'll be able to see cycle effect in the series. Table 6.3 is how you come up with seasonal index for each quarter. Okay, you average SF for each quarter and normalize it. Okay. The way you interpret seasonal index is like, if you have index of 0.79, 1.20, 1.11, and 0.88. You see that for quarter 2 and 3, you have high season, and 1 and 4, you have low seasons. If you multiply each by 100, you sum this value to have a year total of 400 years. It reflects that you expect 79.7 units to occur in quarter 1, 120 occur in quarter 2, 111 in quarter 3, and 88 in quarter 4. That's why it sums up to 400 values. And you can also use seasonal index, each of the index, to extend to have a yearly sales. Okay. For example, suppose that the values of private housing start in quarter 1 is 258.4. Okay, you dimensionalize the data without the effects. Your sale would PSS should be 324, right? This is dimensionalized data, and out of 324 for 1 quarter, you multiply it by 4, because this is without the effects of the seasonality, right? You multiply it by 4, you get a yearly data of PSS to be 1,296.86 units. Okay, so this is how you make a projection of a yearly private housing start using just only the actual data for a particular quarter and the corresponding index for that quarter. Now, let's find a long-term trend, the second component in the series. The long-term trend is estimated from using the CMA or the decentralized data of variable to be forecast. Okay. Let me ask you why we use CMA, not using the original time series. Can anyone be able to tell me? Because a typical time series, right? You have, okay, you can, from previous chapter, you can fit a linear trend to this series, right? In chapter 4, So this is a trend regression. But in decompositions, the recommendation is not to use the YT, but we use CMAT. Okay, to come up with the trend. And like you see, CMA is the TC, right? You get it off short-term fluctuation. You're gonna have a very smooth line. Okay, so when you fit the trend line to this data, it's gonna be more accurate, right? As compared to using the original series and come up with the trend. So that's why we prefer CMA, not YT in this models. And based on using trend regression, you come up with PSS CMA trend to be 237.51 plus 0.313 times. This is the time index. So you run CMA with the times index. 1, 2, 3, 4, and so on. Come up with regression models here. So let me show you how to come up with the trend values. Yeah, the trend. Second component. And you can see clearly that the linear trend would fit the CMA very well because this is a linear relationship, right? You see a straight line here. So that's why I apply a trend regression to this model to represent a trend in the series. Okay, let me bring the CMA, make a copy of CMA and paste it on the new worksheet. Oops, I need to paste it in numbers. Okay. Now I do not need the two rows without the data, so I just want to start period number 1 to be correspond to 2.98. So this is the times index. I write the index in chart. Okay. And have 1, 2, 3, and so on. Okay. Now, you can calculate the equation by hand to come up with B0 and B1, but I would prefer to use tools like data analysis of, SPSS or JABS to come up with the model for me. So let me use data analysis and run a trend regressions. So I run typical regression models. Okay, the Y will be the CMA. And the X will be the time index. Okay. And the first cell contain labels. Okay. You can also look at the residuals and so on. But I want to just only come up with the model to show you. So I skip the proof of validity of the models, okay, in these situations. But you can do it if you like to. Anyway, R squared 0.99 is valid, right? Definitely valid. Okay, you can check the rest on your own. But I will make a copy of these models to be used. Okay, the two values. And paste it somewhere here. Now I have the trend. Okay, so the trend for CMA is actually this one plus the index, right? Times this one, the slope oops, something wrong with C4, no, not this C, this one. That's C4. Okay. And if I want to forecast for the next 6 period here, it's full screen. I can just drag the cells. So this is my trend. So I make a copy of these values. Go back to sheet number 1 and put it starting from these values, right? Here I come up with the trend. If you want to see how it look like in the graph, you can just hide the two values and plot the sales original series, the CMA, and the trend. You see nice picture of the actual data, the CMA, and the fit line. Okay, and the its projections 6 period ahead here. The reason I have 6 values in the forecast because I have to forecast for September Q3 and Q4 of 2021, and then make a forecast of the full quarter ahead here. Now I have the trend and the cycles. Sorry, the seasonal effects already. Let's go back to my lecture note here. When you look at a graph, you see original series in the dashed line. You see CMA, a long-term fluctuation around the trend line, and the trend itself, the CMA trend. The next step is measuring the cycle component. Okay, cycle component over time series is the extend wave line movement about a long-term trend. And it is measured by using cycle factor of CF, and definitely CF is CMA. CF is CMA over CMA trend. You can write CMA as the TC, right? Equal to CMA is the T and C, long-term movement over the trend. Get rid of the trend above and below, you get just only the effect of cycle left. And if it's greater than 1, it means that your sales is above the trend line. And if it's less than 1, it's below the trend line. Let me explain a little bit more on the cycle. This is the most difficult component to estimate. Okay. Why is that? Because you need a long enough historical data, right, to see cycle effects. And in theory, you should have the same length and the same amplitude for each cycle. Okay, let me write down. This is one cycle. one cycle. Am I right? This is one cycle. It's one cycles here. So in practice, you should have the same equal length and equal amplitude in terms of expansion length and recession length. But in reality, it's a bit difficult to come up with equal length because of the random nature of the business, or due to different business circumstances years after years, right? So in practice, you don't have the same links. And you can see clearly that when you go back and look at here, okay, you see the movement along the trend lines with different in length and amplitude, both on the expansion and recession time. So it'd be difficult to come up with, especially when you have to forecast the cycle during the turning point. You move up, and then start to be saturated, then go down. It'll be difficult to come up with, okay? You have to maybe study the previous cycles and then try to make adjustment for the next turning point. Like I said, it is the most difficult component in the time series to analyze and to project into the future. But if you study it carefully, it may help you to understand the situation that the company is running into, okay, in the next 1, 2, and 3 years. So what do you do when you want to come up with the cycle values? You might have to, one approach, sorry. At least how many years? It actually depend on type of business, okay? But definitely, when you correct data, I would prefer more than 5, 4, 5, 6 years, maybe 10 years, 20 years. It depends. Because I think all of the time series that we practice up until now, you don't see clear cycle, right? So that's why when you do the term project, I would prefer that if you want to look at the cycle, you need long enough historical data. So how do you do when you want to make a guess for the next cycle? Okay, you can use your knowledge, experience, or someone else's experience about the business situations. We create. And then, so this is YT. And suppose that you get rid of short-term fluctuation, you see a cycle in your data. Okay. So this is one cycle. Erase it one more time. Okay. Now, here is one cycle, right? We write a long-term trend. So if you happen to make a guess or not guess, estimate for the cycle for the next maybe 1 or 2, 3, 4 period, you might want to determine the length and the amplitude, right? From this point to the peak of the cycle, and you can estimate here, and then draw the values. If you get it off the trend, you're gonna see the picture like this. And now you have a flat trend. And then you can determine the cycle, right? Something like this, okay? So these are the value that you estimate out of one here. So you read this value and plug into the cycle. So this is how you do it. But like I said, if you have long enough data, you might end up having more than one cycle. And based on business situation, you know, the cycle for each period is not equal, right? You might need to not using just only the last period, but you might have to average. You know, you see the length from this point up until the peak for the last period, and for the previous period here, and from here. And then you might have to average them to come up with the, you know, the length between the beginning of the cycle to the peak of the cycle. So it really depends on how long you have for his historical data, and the approach that you apply to make judgment for the cycles in the period that you would like to have to make forecasts. Okay. So this is one thing that you can do. The big advantage of this approach is you can estimate the turning point. Okay, when it's gonna be turning point. Okay. But the difficulty is, you know, you have to have long enough data. In practice, many times you rely on the forecasting software. Okay, suppose that you collect not long enough historical data and you see that it's gonna be something like this. Okay, or not like this. Maybe let's go. You calculate the cycle and it's increasing something like this. Okay, if you want to forecast for the next 1, 2, 3, 4 period, you can fit forecasting models and make prediction easily, right? Okay, this is done by software. Okay, you get some kind of shortcut and make a forecast of the cycles. But you have to be careful when you apply the software, okay, to help you to come up with the cycle effects here. It cannot project the turning point. So if the data here is at the turning point, or it come close to the turning point, and it will go down here. When you apply Forecast X or other software to make a forecast, it will keep projecting the cycle to be increasing here, not going down. Okay, so this is This is the effect that software cannot recognize. The turning point. So you have to be very careful and make your judgment whether it's arrive at the turning point or not. If not, you can still use the software. But if it is the turning point, you might have to use your experience and determine the historical data and make judgment on your own. So looking at the length and the amplitude of previous cycle may help you to anticipate the next turning point in the current cycle and may hint you to give a future direction of the cycle component. Okay. When you make judgment about the cycle, you might have to go back on the maybe econometrics studies, economics class actually, to look at the business cycles. And you see that you have the bottom, okay, the beginning trough, and then you go to the expansion period, right? You know, the way you determine the expansion period is when you have maybe 3 consecutive quarters that you increase in your sales, right? And then when it go to the peak and start to decline, this is go to the recession or contraction phase or period. And the way you determine that it arrive at your business arrive at the recession period when you have a drop in your sales, drop in your demands for the next 3 consecutive period of quarters. So this kind of knowledge will help you to determine the cycle component for the forecasting period. Yeah. Okay, but like I said, in theory, each period should be the same, both the length and the amplitude, but in practice different. So you need real data and do the study. Okay, let me do the calculation of CF and then use forecast X to make projection of cycle. The C. The C is actually the CMA, right? The TCs over the trend. Oops. And when you look at the time series, it seems that, well, the cycle effect is not that clear. And if it has a cycle, I think you still, it's on the increasing, you still use the program to help you to come up with the forecast values, the situations. So I will make a copy of this series and put it in the new sheet. Okay, let's use the data here. This is not in bold. Okay, get it off the blank cells here. Okay, now I have a series of cycle. I can mark the series and ask for X to help me. There's no periods, right? So skip it. want to forecast 6 period ahead. Actually, you can use any of the periodicity here because not involved in, you can look at the data to be either a monthly, quarterly, or annually data. Okay, go to, if you look at the data, well, and you can see that there's no trend here. You can maybe try to use technique like SES or moving average to come up with the forecast values. But if there's a trend, you may want to use like holes or other models. But what I do is to use the AI commands in ForecastX. This is the broadcast professional forecast. Okay, I ask ForecastX to come to fit all the models to this series for me and come up with the one with lowest errors. Okay, so I ask ForecastX to do it here. Go to statistics. Well, you can skip the statistic and use the fit values tables here. And these are the 6 values of the forecast. Okay, even though the accuracy is not that good, but I will use this one as an example. So I have this one and press it here for the 6 values of the forecast. I can do the same when I go back to the cycles here. I press it here. Okay. Now I have all the forecast value of cycle factors. Let me hide all the data. Okay. So I come up with CF, okay, which is CMA over CMA trend, and then I ask the software to fit the data for me. This is an example of the cycle for PHS. You see lots of fluctuation around the trend line. For this particular example, when we use ForecastX to come up with the model to capture the values. Whole exponential smoothing is selected with the forecast values. Okay. And I said be careful because it will not pick the turning point. But if you believe that a turning point is unlikely, you can insist to use the hold. Okay, another forecast that ForecastX come up with is the forecast by using Box and Jenkins, and Box and Jenkins model in chapter 7, and this is the forecast values here. Okay. This is the explanation that I already give you, so I want to skip it. Now, after you get a forecast value of cycle component, when you make a forecast of the data, you bring them together, you bring trends, seasonal effect and cycle effects to the calculations. And this is multiplicative form. So what do? Okay, you have the forecast values to be from the trend multiplied by the cycle TC multiplied by S. And the I is 1 because we do not forecast that it's going to be irregular variation, right? So So this is the forecast values for historical data, and this is for the out or for the real period that you like to make a forecast. Okay, so you multiply T, C, and S together, come up with the forecast values. So let me hide these variables and plot sales or actual value versus the forecast value using decomposition. You can see that the forecast fit the actual data very well. Okay, so this is how decomposition model can be built and used to make a forecast. It's very accurate here. So the reason that I use Microsoft Excel is to help you to understand each step of the decomposition procedure. Okay. Once you understand the concept and you want to use it in practice, you can ask ForecastX for help. Okay, here is the area that I like to make a forecast, run a forecast, and make a projection of 2022 for 4 quarters here. I go to ForecastX. And since the format of the period is the standard format, so ForecastX can recognize it and the quarterly data. Right? Here I like to make a forecast of 4 period here. And go to forecast method here, and I can select decomposition. And in decomposition, like I said, there are 2 approaches. Here we are using multiplicative form. Okay, and inside is the selection of the trend line. Okay, I see that there's a linear trend. That's why I select trend regressions. But you can ask ForecastX to come up with the trend by using Box and Jenkins, by using the average values, by using Holt, by using SES, okay, or by using Procast. So you ask ForecastX to come up with the best trend models for you. Since I see a linear trend, let me use linear trend here. So let's go to statistics. You can select more statistic and check on root mean square until's. And go to the report, go to audit, fit value tables, and run ForecastX. And here is the output. Okay, it looks similar to the one that we come up with by using Excel. Right? Accuracy of this model is pretty good, 94.79%. MAP is around 4.58%, which is not that bad. Deals around 0.2. Okay. And here is the details of the calculation. You have original time series. You have CMA. Okay. So you have to perform MA first and average the MA to come up with CMA. And then you have the system index. Okay. This is 1.27, 1.01, 0.73, and 0.98. Is exactly the same as system indexes that we calculate. Right, 1.727, 1.01, 0.73, and 0.98. Okay. So if you want to use these indexes, and you can make a copy and bring it and deserialize the data and use other model to fit the data. And this is the forecast values. Well, it seemed that it used trend regression here, and this is the forecast values. See that there's no, sorry, this is the cycle factor. There's no effect of cycles here. They are pretty much close to 1, right? There's no effects here. You get 79% accuracies. You can apply different trends. Okay, let me see. Let's rerun forecast X and go to decomposition. Well, maybe this time I will try to use whole models. I think you get marginal improvement of the accuracies. Here you have 95.73% values of R square, and you have 4.38% of MAP as compared to 4.58, I think. Yeah. So it's just a minimal improvement. So you can either use the trend regression or use whole model to forecast the trend in the decomposition models. So it's quite easy to come up with the output. And with 4 component part in the series, I think it's very easy to comprehend, okay, the models and to use the model to make a forecast of future values. So that's why it remains popular now today, still. What is the formula for cycle? In this situation, if you want to see, there's no output, there's no model represent here. I don't know whether you can see it in the in forecast X or not. Okay, for this one, whole winter model is selected to make a forecast of the cycle. Okay, this is whole models. I use broadcast, so it select whole winters. The reason for selecting whole and winter may be logical or not logical. It depends on how the model look, how the forecast model software look at the data. But it picks whole and winters. And you know that if there's no seasonality in the data, the models, the whole and winter model will reduce its form to be just only the whole models. And if there is no trend, it will reduce to just only SES. ครับผม Okay, let's go back to my lecture note and try to finish it. So make a forecast T times C times S at time I, and I is always 1, as we do not forecast irregular variations in the futures. We're not gonna forecast that it's gonna be a second, maybe other pandemics occurs, right, in the next 1, 2, 3, or 4 years. Okay. It happened once in the past, it's not going to happen again in the future. This is the way we assume when we make a forecast. And use PSS data and apply decompositions. When you run historical and whole out, you have 64, 65 and 68 MSE, which is very close to each other. So the model is quite valid here. And this is a picture of original series and the forecast values using decompositions. When we apply DCS for decomposition for DCS series, and you can see that the dashed line represents the original DCS series. CMA is the dark line here, and you see that this is also reflect a cycle in the data, and you have CMA trend. And again, you see that each period of the cycle is not the same. Okay, the decomposition model come up with seasonal index of 0.961 for quarter 1, 1.10 for quarter 2, around 1 for quarter 3, and 0.93 for quarter 4. And you see that Q1 and Q4 here are low seasons. Okay. Q2 is the high season and Q3 is about the average. And this is the cycle line here. And you can use ForecastX to make a forecast. But like I said, be careful for the turning point. When you apply decomposition forecast, you multiply the trend, the index, and the cycle factors, come up with the forecast values. Seem to be very good here. But anyway, let's go back to chapter 1 up to chapter 5. You have naive, you have winters, you have whole with seasonal adjustment, you have simple regression with, again, seasonally adjust DCS as a function of DPI. You have multiple regression models. And you can check on the historical RMSE and the whole RMSE. So based on your observation here of these outputs, which model that you are going to select to be used for your forecasting purpose? Which model?
Is it simple regression?
Yeah, simple regression because it has the smallest historical and whole RMSE. It's 96 and 87. Very good. I think the reason that simple regression fit very well to historical data and the whole is because you select the very important independent variables, the disposable personal income that's highly related to the sales, right? The domestic car sales. This is one thing. The second thing is that you get rid of seasonality, which is the short-term fluctuations ahead of the time. So when you apply regressions, it fits the data very, very well here. That's why you get errors to be very small. Time series decomposition, it seems to be fit the data, but with historical RMSE and whole out, it's huge as compared to simple regression in this situation. So you pick model number 4 to be the best one. Another example is the gaps series. You see the gaps here, you have definitely strong seasonality and strong trend. And the trend is not linear. You have a curve here. So your job in decomposition is to come up with the model to capture a nonlinear trend in the gap. Okay. Seems that the trend of exponential values of time index is the best one. So, and after you come up with the trend, you can divide the CMA with the trend, and you come up with cycle effects in the gaps. And you can make a forecast of the cycles here. And this is the values, okay, between original series and the forecast values seem to fit each other very well here. So I expect R squared to be close to 100, maybe 95 subs. Anyway, let's look at the outcomes from 6 models, starting from naive with 4 period lags, winters, whole exponential smoothing with seasonal adjustment, regressions, okay, with decentralized data, multiple regression, and time series decomposition. So which ones among the 6 models should be selected to be used for forecasting purpose? Which one this time for the gaps?
Whole.
Yeah, whole exponential smoothing, which again seasonal adjustment. It gives more or less historical and whole R, let's see, 42,000 and 74,000. Decomposition, model fit historical data very well, but it fit whole out data poorly. So you have to maybe put big question marks on the time decompositions and multiple regression also, The reason is that when you look at the data, this situation, you don't have a constant variance in the data. When you look at the variance, okay, and if you're it's gonna cause you problems. Why is that? Because the higher the value or the as time move on, okay, the bigger the values, right? Because with bigger variations. This is the case that we have to deal with. Okay, to make it have constant variance, so we can make a forecast with consistency in terms of the model's accuracies. So what should we do before we run all the model to the data? We should take a log of the gap. We shrink the values. As you know, that is what? 1 log base 10 log. You can take a log 100 is 2, right? You shrink the scale of the data. It will help you to come up with a more appropriate forecasting model. But once you make a forecast, don't forget to take a log, take a log out of the series to come up with the final forecast. Something like this. I forget how to do it, but you unlock the series to come up with the final forecast. But well, I think this one is a bit complicated and beyond the scope of this text. So most of the time you deal with a series with constant variance. Not something like this. Okay, this is toward the end of chapter 6. Is there any questions to ask me? By now you know how to decompose the trend, the seasonal effect and the cycle effects. So now it's your turn. I think I will give number 10. This is homework number 10. What I like you to do is to develop the composition models for Costco time series. Okay. Using Excel. Okay, not forecast, because if you run forecast, you don't have to do anything, right? But I like you to go back to the procedure of the composition models, okay, and to understand more how to build up the models and how to use the model to make a forecast. So you use Costco time series, an example, the time series that we used for previous examples. Homework number 9. You can just use the revenues. You have the period and the revenues, and then you can run the composition procedures as I did. Okay. And not next week. Okay, I give you like you guys 2 weeks, because next week still be on holidays, right? We still in the Songkran holidays weeks. So let's skip next week and come back on the April 22nd, right? We will move to chapter 7, Box and Jenkins, and toward the end, okay, early of next month. So is there any questions? Feel free to ask me now, or if not, I will let you guys go and see you after Songkran holidays. มีคำถามไหมครับ Any questions?
I have a question regarding the final project.
ครับผม
When it will be announced, like when will you assign it?
Yeah, actually you can start doing the term project right away. Your job is, together with your friend, right? Come up with the team, and then you can select time series of interest. Okay, you can go out and search for variable of interest. Okay, and then you can start running forecasting model, different forecasting models. Your job is like this. Suppose that you are within the firm, and I'm the executive. Okay, I'm the CEO, and I ask you guys who are in the maybe business development division to come up with the forecast values of the company sale next year. Now it's your job to go back and run the analysis and bring back to me an executive report. Okay, what are the forecast values, right? And you have also to give me some conclusions, remarks of your forecast values. Right? So this is what you have to do for the term projects. And you learn many models already. Okay, you can apply several relevant models and try to make best forecast out of these models.
Okay, thank you.
The due date, if you have a group of two person, you have free choice to select quarterly data or monthly data. But if you have a group of 3 person, I require you to have only monthly data. Okay. Because group of 3, you need more effort, right? You have to put more effort to deal with, the data, the forecast model for the data. And the due date. The due date is 1 week after the last day of your final exam. Okay, if the last day is like May 20, the due date is on 27th. Okay. We can talk about the due date maybe during the last class. Next one. I don't think that it complicated. Okay, you can team up with Corinne. Corinne, do you have group already or not?
No.
Not yet. Yeah, you can talk. You guys can talk together and can team up. And for homework number 9, yeah, you can resubmit. Okay, you can submit the works. Okay. I don't think that we have to make up for the class for the Songkran because it I think the calendars cover Songkran already. We have already make up class because today is class number 12, right? Normally we're gonna have like just only 14 class a term. But after Songkran, we still have 3 more. I don't know who you are ครับใครครับคนนี้ครับ Can you talk to Corinne and you guys can team up, as a team and do the term project together. But if you like to do it alone, feel free to do it. That's fine. In the past, there are many students select to do term project alone. Okay. So if there is no further questions, enjoy your holidays at home actually. But if you have to go out, go traveling, watch out for your health. Okay, always wear mask and make sure that you have booster vaccines already. Okay. Okay, Cup, and thank you for all you guys and see you after Songkran Festival. Bye bye.
Thank you ค่ะ
ครับผม
Thank you.